You flick a light switch, light comes on. Seems simple, right? But what if I told you there are these unseen forces, these miniature dramas unfolding inside your circuits, shaping how power actually flows? Today, we're taking a deep dive into the secret lives of two really fundamental components, inductors and capacitors. Honestly, they're at the heart of nearly every electrical system we use.
Hmm.
Yeah, these aren't just obscure parts, they're kind of the unseen choreographers of current and voltage, from your phone right up to the massive power grids. Our mission today is, well, to unpack their unique effects in both direct current, DC, and also alternating current, AC circuits, and hopefully you'll see why understanding them is pretty crucial for anyone who's curious about how electricity really works. We've got some fantastic instructional material from places like NAIT and SIT that breaks these concepts down with real-world relevance, which is perfect for this kind of deep dive. So let's pull back the curtain on our first star player, the inductor. Now, if you imagine a circuit that's purely resistive, like just a wire and maybe a simple light bulb, when you flip that switch, the current flows instantly. Bang! But if you throw a coil of wire, an inductor, into that path, well, something really fascinating happens. It's like the current suddenly hits a speed bump. Or maybe, more accurately, it hits something that resists change in current. It just absolutely refuses to let current, appear or disappear instantaneously.
That's really the essence of an inductor. It stores energy in a magnetic field, and its very nature is to oppose any change in the current flowing through it. And this inherent resistance to change creates what we call a time constant, which we usually symbolize with T. For an inductive circuit, we calculate it as L, that's the inductance divided by R, the resistance. And this time constant, well, it's your benchmark for how quickly things settle down.
Okay, so how quickly do things settle then? What does that time constant really tell us about the speed of this current buildup?
Well, after just one time constant, the current has already made a pretty significant leap. It's reached about 63.2% of its final steady value. And here's the crucial insight. This rate of change isn't, linear, it doesn't go up in a straight line. Each time constant after that covers about 2/3, roughly 63.2% of the remaining gap to that final value. So it's a general rule of thumb, and it's a very good one. After about 5 time constants, you're essentially at full stable current. It's a fundamental principle.
Right. Okay. 5 time constants. That's a great way to think about it. It's about the rate of change getting smaller each time. So if I have a circuit with, say, high resistance, does that mean the current settles faster or slower? And what about a high inductance? What does that do?
Great question. So if you have high resistance R, it actually shortens the time it takes to reach that steady current. Why? Because the final steady current value itself, determined by Ohm's law, VR, will be lower. So resistance has an inverse relationship with the time it takes, even though it's in the denominator for the time constant calculation itself, TLR. Higher R means smaller t.
Oh, okay. So higher R, shorter time. Got it.
Exactly. But if the inductance, the coiliness, as you put it, is high, then the induced counterelectromotive force, the CEMF, is also higher. This stronger opposing force means it takes longer for the current to overcome that opposition and reach its steady value, so that shows a direct relationship. Higher L means a longer time constant.
Okay. That resistance to change, that sort of slow dance of current, makes sense when we're applying power. But you mentioned drama earlier. What's the dramatic payoff when we suddenly remove that power? What happens when you, open an inductive circuit?
That is where we can get the inductive kick.
Yeah.
It can be quite dramatic.
Yeah.
When you open an inductive circuit, that magnetic field, which has been busy storing energy, collapses. And it collapses incredibly rapidly. This sudden, drastic change in current from its steady value, maybe down to 0 almost instantly, induces an extremely high voltage across the opening contacts of the switch.
Yeah.
Just as an example, imagine a 0.2 Henry inductor, which isn't huge, carrying 4 amps. If that current were to drop to 0 in just 0.4 microseconds, which is incredibly fast.
Microseconds, wow.
Yeah, it could theoretically generate an induced voltage of 2 million volts. That's 2 megavolts.
2 million volts. Okay, that sounds like an electrical horror movie right there. Is that why sometimes you see a little spark when you unplug, say, a vacuum cleaner or turn off a big motor?
Absolutely. That little spark you see is exactly a miniature version of this inductive kick. On a larger scale, this kind of high voltage can cause really severe arching at switches. It can damage components, weld contacts together, and it's definitely a safety hazard. Fortunately, there's often quite an elegant solution: discharge resistors.
Discharge resistors, okay. How do they help?
Well, by connecting a resistor in parallel with the inductor, you provide an alternate path for that current to flow when the main switch opens. So instead of trying to jump across the air gap of the switch, the current flows through the resistor, dissipating the stored energy more gradually. This drastically reduces the voltage spike. For instance, using a simple 100-ohm discharge resistor in that 2 megavolt scenario could potentially bring that peak voltage down to a much more manageable 400 volts.
Wow, quite a difference.
A huge difference. The current gets a safe path, no lightning show across the switch.
So what does this all mean for you, listening? Well, understanding this helps you see why specialized components and careful design are needed to protect critical electrical systems. It's all about preventing those sparks, preventing damage, and ensuring safety in everything from, big industrial machines right down to your everyday appliances. It's not just about turning things on and off, it's about managing that stored energy gracefully. Okay, so that's the inductor story, a real gatekeeper of current, resisting change, and sometimes unleashing quite a shocking kick if you're not careful. But what about the other unsung hero in our circuits? If inductors are constantly wrestling with current, there's another component that has its own fascinating dance with voltage. How do capacitors fit into this hidden drama?
Right, capacitors. If inductors are about current, capacitors are really about voltage. You could almost call them the voltage whisperers. Unlike inductors that resist current change, capacitors store electric charge. And in doing that, they effectively resist changes in voltage across them. Think of them like tiny, rechargeable, temporary batteries. They're always ready to absorb or release a burst of electrical energy.
Okay, storing charge. And we measure that charge in coulombs, right? What exactly is a coulomb in, practical terms? Is it a lot?
That's right, coulombs, symbol C. And yes, 1 coulomb is actually a huge amount of charge. It's roughly 6.24 times 10 to the 18 electrons. But practically, we can think of it in terms of current flow. 1 coulomb is the amount of charge that flows past a point if you have a current of 1 ampere flowing for 1 second. So if you have, say, 2.5 amps flowing for 2 seconds, you've moved 5 coulombs of charge. Simple multiplication, Q equals I times T. We can also relate charge directly to the capacitor itself using Q equals C times V, where C is the capacitance in farads and V is the voltage. So for example, a 50 microfarad capacitor that's 50 millionths of a farad charged up to 22 volts would store, let's see, 0.0011 coulombs, or you could say 1.1 millicoulombs.
Okay, 1.1 millicoulombs. So how does this charging process actually work in a DC circuit? Does the current just instantly flood in until it's full?
Not quite instantly, no. It follows a similar kind of curve to the inductor current, but now we're looking at voltage. When a capacitor is first connected to a DC source, assuming it starts empty, current rushes in quite rapidly. Electrons pile up on one plate, making it negative, then they're pulled off the other plate, making it positive. This separation of charge creates an electric field between the plates, and that's where the energy is stored. But as the capacitor charges, the voltage across it builds up, and this voltage starts to oppose the supply voltage, pushing back against the incoming current. Eventually, when the capacitor's voltage equals the supply voltage, the opposing forces balance and the current flow spents. At that point, we say the capacitor is fully charged.
And then discharging is just letting those electrons flow back.
Exactly. If you disconnect the supply and provide a path between the plates, maybe through a resistor, the electrons rush back from the negative plate to the positive plate until the charge is balanced again and the voltage drops to zero.
And I'm guessing just like inductors, capacitors have their own time constant that governs how long this charging and discharging takes.
Precisely. In these resistive capacitive circuits, or RC circuits, the time constant, T, is calculated very simply. It's just R, resistance, multiplied by C, capacitance. T equals R times C. And yes, that same 5-time constants rule generally applies. It takes approximately 5-time constants for a capacitor to fully charge up to the supply voltage or to fully discharge down to zero.
Okay, so if the inductive time constant described how the current built up towards its max, what does the capacitor's time constant describe? Is it the charge or the voltage or?
Good clarification. For a charging capacitor, the time constant describes how the voltage across it increases. During each time constant, the capacitor voltage increases by 63.2% of the remaining voltage difference between its current voltage and the maximum supply voltage. Now, interestingly, while the voltage is rising like this, the current flowing into the capacitor is actually decreasing. It starts high and drops off. In fact, during each time constant, the charging current decreases by 63.2% of its value at the start of that interval. So these were inversely related curves.
Ah, okay. So voltage ramps up, current ramps down.
Exactly. And to give you a quick example, if you had a 200 ohm resistor and a 15 microfarad capacitor, the time constant T equals RC would be 200 times 0.00000015. which is 0.003 seconds or 3 milliseconds. So applying the 5-time constant rule, it would take about 5 times 3 or 15 milliseconds for that capacitor to fully charge.
15 milliseconds. Pretty
Yeah,
quick. And similar to inductors, if you change the resistance or the capacitance, you change that charging or discharging time.
absolutely. Higher resistance means less current can flow, so it takes longer to charge. Higher capacitance means it can store more charge, so it also takes longer to fill up. It's a direct relationship in both cases for the RC time constant. Bigger R or bigger C means a longer time constant, longer charge discharge time.
Okay, this raises a really important question then. Why does this storage and release of energy actually matter? What practical impacts does this sort of hidden voltage drama have in our, daily lives?
Oh, it has huge impacts. Think about some common devices. A camera flash, for instance. That bright burst of light comes from a capacitor rapidly discharging its stored energy through the flash tube. Or think about car airbags. A capacitor's rapid discharge provides the jolt needed to trigger the chemical inflation mechanism almost instantly in a crash. Even inside your electronics like your computer or TV power supply, capacitors are constantly working to smooth out ripples or fluctuations in the DC voltage, providing a more stable power source. They're everywhere, really, managing energy flow, timing circuits, filtering signals, just silently orchestrating the ebb and flow of charge.
Right. So we've seen how inductors and capacitors behave with steady DC, slowly building fields, storing charge, resisting change over these time constants. Now, let's flip the switch literally to AC. Let's turn up the frequency and see how these components behave when the current isn't just steady, but it's constantly reversing direction. What happens when we introduce them to the wild, constantly changing world of alternating current?
Ah, yes. AC is where things get truly dynamic for both components, but especially for inductors. In AC circuits, the current is continually changing direction and magnitude, maybe 60 times a second in North America, 50 times in Europe. And this constant change is precisely what an inductor, with its inherent opposition to current change, reacts to most strongly. It creates an opposition that we call inductive reactance, symbolized as X, subscript L, XL.
Okay, inductive reactance, XL. You said it acts like resistance, but it's more than that. How does this opposition fundamentally change how current flows in AC? And what factors actually make this pushback, this reactance, stronger or weaker?
That's a key distinction, yes. While XL is measured in ohms, just like resistance, it isn't resistance in the traditional sense of dissipating energy as heat.
Hmm.
It's an opposition specifically to the rate of change of current, and it arises because of that constantly induced CEMF, the back voltage. And critically, it only exists in AC circuits. In DC, once the current is steady, there's no change, so the inductor just acts like a piece of wire, ideally with zero opposition beyond its basic resistance. XL disappears.
Right, only in AC. So what makes it stronger or weaker in AC?
Two main factors influence its strength. First, the inductance, L, of the coil itself. A higher inductance means the coil is better at generating that opposing CEMF for a given rate of change, so you get a higher XL. You can think of it as a bigger, more powerful coil having more reactance. Second, the frequency F of the AC supply. A higher frequency means the current is changing direction much faster. This higher rate of change induces a larger CEMF and therefore results in a higher XL. Essentially, the faster you try to make the current flip-flop back and forth, the harder the inductor pushes back against it. It's a direct relationship for both L and F.
Okay, so the inductor is constantly pushing back against these rapid changes in AC current. How does that actually affect the timing? Does the current manage to keep pace with the voltage, or does something, well, interesting happen with their synchronization?
Something very interesting happens. It creates a specific time delay or phase shift.
Hmm.
In a purely inductive AC circuit, meaning only inductance, no resistance, the current, which we can call IXL, actually lags behind the voltage across the inductor, VXL. And it lags by a very specific amount, 90 electrical degrees.
90 degrees lag, so the current hits its peak after the voltage does.
Exactly. The voltage peak happens first, then a quarter of a cycle later, the current peak occurs. We often use something called phasor diagrams to visualize this. Imagine the voltage and current as rotating arrows, or vectors. In this case, the current arrow would be trailing 90 degrees behind the voltage arrow as they rotate, like it's always playing catch-up.
Okay, lagging current. So if we connect this to the bigger picture, is this lagging effect useful? Why is it important?
Oh, absolutely vital. This lagging effect is fundamental to how AC motors work, for example. Controlling this phase shift helps control the motor's operation. It's also key in filtering circuits. Inductors, because their reactance increases with frequency, can be used to block high-frequency noise while letting lower frequencies pass through, or vice versa, in combination with other components. Think audio equipment, power supplies.
Right, filtering. Okay, so we've established that inductors make current lag behind voltage in AC circuits by 90 degrees. Now, capacitors. What do you think they do when the voltage is constantly swinging back and forth in an AC circuit? Do they create an opposition too, and how does it compare?
They absolutely do create their own opposition in AC, yes, but it's called capacitive reactance, or XC. And mirroring their fundamental nature, it's specifically an opposition related to voltage change. They don't like voltage changing quickly across them. Just like XL, it's measured in ohms. And critically, it also only really exists in AC circuits because it requires that constantly changing voltage to keep current flowing back and forth through the capacitor, so to speak. In DC, remember, once a capacitor is charged, it acts like an open circuit, essentially infinite resistance, blocking steady current flow.
Okay, interesting. So XC, capacitive reactance, opposes voltage change. What factors influence its strength? And crucially, do they work the same way as with inductors, or is it different?
It's different, and this is a really key contrast. Again, two main factors, but for capacitors, they're inversely related to XC.
Mm.
First, capacitance. A higher capacitance means the capacitor can store more charge for a given voltage. In AC, this means more charge can flow back and forth easily during each cycle. More charge flow implies less opposition, so higher capacitance C means lower capacitive reactance XC.
Okay, inverse. Higher C, lower XC. What about frequency?
Same inverse relationship. If the frequency F of the AC supply is high, the voltage across the capacitor is changing very rapidly. This forces the capacitor to charge and discharge very quickly. This rapid charging and discharging means a lot of current is flowing back and forth. More current flow means less opposition, so higher frequency F also leads to lower XC. So, you see, the faster the voltage changes, the easier it is for the capacitor to pass the AC current. It's the exact opposite behavior compared to an inductor.
Wow, okay. Exact opposite. So the inductor's reactance goes up with frequency, the capacitor's goes down. And if the inductor made the current lag, what does the capacitor do to the timing? Does it lead?
Precisely. Given that everything else seems inverted, it's maybe not surprising that the phase relationship is also inverted or opposite. In a purely capacitive AC circuit, the current, let's call it IXC, actually leads the voltage across the capacitor, VXC, by 90 electrical degrees.
Leads by 90 degrees. So the current peak happens before the voltage peak.
That's exactly right. The current hits its maximum value a quarter cycle before the voltage does. On those phasor diagrams we mentioned, the current arrow would now be 90 degrees ahead of the voltage arrow. It's leading the dance, essentially.
So inductors lag, capacitors lead, both by 90 degrees. They really are opposites in AC.
They truly are. It's a fundamental duality in AC circuits.
And this leading current effect from capacitors, I assume that's just as important practically.
Absolutely. Think about tuning a radio. Often you're adjusting a variable capacitor to change its reactance, which, in combination with an inductor, allows the circuit to resonate at and select a specific radio frequency. Or in power supplies, again, they help smooth out voltage, but their ability to pass AC current readily is also used in filtering applications. And maybe one of the biggest uses, power factor correction. Large industrial motors are highly inductive, causing lagging current. Utilities often use large banks of capacitors which cause leading current to counteract the inductive lag, bringing the overall current back in phase with the voltage on the grid. This improves efficiency and reduces energy costs.
Right, balancing things out. That makes sense. So let's try and tie this all together. We've seen how these two components play these wonderfully opposite roles, especially in AC circuits. One causes current to lag, the other makes it lead. And it seems to boil down to this fundamental difference, right? Inductors resist current change, capacitors resist voltage change. Is that the core takeaway?
That is absolutely the core takeaway. That single principle dictates almost all of their nuanced behavior in both DC and AC circuits. It explains the time constants, the inductive kick, the reactances, and those crucial 90-degree phase shifts in AC. It all stems from what they inherently resist changing.
And this behavior, it's not just like a qualitative thing, it's precisely calculable.
Oh, definitely. It's all very well defined by mathematical formulas that engineers and electricians use constantly. For inductive reactance, that formula is XL equals 2 times pi times frequency times inductance, or XL equals 2FL. You can see frequency F and inductance L right there in the numerator, showing that direct relationship we talked about. Higher F or L means higher XL. For capacitive reactance, the formula is XC equals 1 divided by 2 times pi times frequency times capacitance, where XC equals 1 to FC. Here, F and C are in the denominator, clearly showing that inverse relationship. Higher F or C means lower XC. These formulas are absolutely essential for predicting how circuits will behave and for designing systems that work correctly and safely across, well, every electrical application you can imagine.
Exactly. These principles aren't just abstract theory, they are literally the bedrock of electrical and electronic engineering. From the hum of an electric motor starting up to the filter that gives you a crisp Wi Fi signal, inductors and capacitors are constantly at work, shaping the flow of energy and information in ways we often take for granted. They really are the unsung heroes defining the very characteristics of our modern electrical world. So, to recap today, we explored the really dynamic world of inductors and capacitors. We saw how in DC circuits, they control the timing of current and voltage, whether it's slowly building a magnetic field or storing up an electric charge over those time constants. And then in AC, they introduce reactance, this frequency dependent opposition, fundamentally altering the phase relationship between current and voltage, causing one to lag, the other to lead by that crucial 90 degrees. So, here's something to think about. The next time you see a seemingly simple circuit or even just plug something in, remember that hidden dance of electrons and fields going on inside. If inductors always try to keep the current flowing just as it was, and capacitors always try to keep the voltage just as it was, what powerful synergy, or maybe what surprising conflict, might arise when you put both of them together in the same AC circuit? The possibilities there are, well, truly electrifying, maybe something to explore further. We encourage you to observe the electrical devices around you, maybe even look up some circuit diagrams online, and see if you can spot these foundational components at work.